Hello, my name is Kylie Taylor, and I'm going to present my IBM Coursera Advanced Data Science Capstone presentation. So I did a stateful LSTM and compared the results of that model against the results of a ARMA model using wave parameter data. So let me introduce my data a bit. The data is collected every 30 minutes for 30 months off the coast of Mooloolaba, Queensland. Measurements span from January 1st, 2017 to December 6th, 2019. This data is sourced from Kaggle.com, which was provided by the Queensland Government Data Repository. There are 6 features on top of date, which is when the observation was recorded, date and time. 6 features on top of that. These include HS, which is the average of the highest third of the waves in a record, Hmax, which is the maximum wave height in the record, TZ, which is zero upcrossing wave period, TP, which is peak energy wave period, peak direction, which is the direction related to true north from which the peak direction waves are coming from, and SST, which is the approximation of sea surface temperature. The use case of this data can be used for predicting future wave cycles and parameters. Forecasts could be given to the Queensland government to set expectations for sea surface temperature and the steady state of ocean waves. This is important because the government could be able to identify abnormalities more easily. This could ultimately protect the residents of Queensland because the government would be able to notice threats and warn people before it was too late, say if there was a tsunami. My solution to the use case is I used Python 3.6 with Apache Spark with code remarks written in a Jupyter notebook in the IBM Waston studio. I imported the data as a pandas data frame and was converted to a NumPy array for computation ease. And 2 models used to forecast the wave parameters was a simple machine learning model, which was an ARMA 1.0, so autoregressive order 1, moving average order 0 model, and a deep learning stateful LSTM. I used a stateful LSTM because this data is time series data and thus depends on state. The 2 models were ran a second time with normalized data to see if it would improve performance at all. So some of my architectural choices. The data is stored in the IBM Watson Studio Object Store as a .csv file. I pulled the data directly from Kaggle and called the data into a Jupyter notebook from the .csv file in the Capstone project folder. The data, again, is important as a pandas data frame. So before I did any analysis, I clearly did data quality assessment. I identified any missing values, which happened to be recorded as negative 99.0. It's clearly missing because no wave height could be a negative height. I removed all the rows that had missing data. That's because I did not know the nature as to why the data was missing, and this was not many rows. I then plotted the series and noticed that the sensors began to have errors in more recent dates. For this reason, I only kept the first 31,000 out of the 47,000 observations. Here are some of my pre-processing steps. I just plotted time series of all 6 features. Again, it's just graphs. And then I also plotted histograms and densities of all 6 features. So the data appears to behave well and have predictable distributions. Most features experienced high skew, which is intuitive, high right skew, which is pretty intuitive for this data. We wouldn't expect large negative skew with wave parameter data. My next step was feature engineering. Initially, I scaled all the data points to a range between 0 and 1. This process still preserved the skew of the data since it is not a normalization process, rather a compression process. Since the data clearly has right skew and not all features are measured in the same units, I normalized data and used this for the second set of models. Here is just summary statistics of the normalized data. My model performance indicators was I used mean absolute error. I did this so I could compare results from the ARIMA model to the results from the stateful LSTM. So here's my model algorithm. The stateful LSTM algorithm uses a batch size of 64, 10 time steps, and 20 epochs. This is some of my model training right here, the code that I've included. Both the ARIMA and the stateful LSTM model use the same train test split sizes of 24,000, 798, and 6,200 respectively. The first stateful LSTM uses 2 LSTM layers with 10 nodes in each layer, then a dense layer as the output. The models use a stochastic gradient descent as an optimizer, a mean squared error loss function, and mean average error and accuracy as the evaluation metrics. This code chunk in here is some of the code I wrote just to develop the LSTM model. I used accuracy to compare how the LSTMs perform from non-normalized data to normalized data, and again ran the same stateful LSTM model with the normalized data. I used an ARIMA model, 1, 0, 0, so autoregressive order 1, integrated order 0, and moving average order 0. So a pretty simple ARIMA model as a simple machine learning model to compare against the performance of the stateful LSTMs. The mean average error was computed between models as well as the EIC. And so the EIC between both models, which showed that the model with normalized data performed significantly better than the model with non-normalized data. To conclude some of my findings from this study, both the stateful LSTM and the ARIMA models performed significantly better with normalized data. The accuracy of the LSTM model increased nearly tenfold, and the AIC of ARIMA was nearly 100,000 points lower. A huge improvement. The stateful LSTM model always performed better than the ARIMA model, as it should. And models with non-normalized data, the LSTM mean average error is about 0.064. The ARIMA mean average error is about 0.095. So again, LSTM performed better. And for the models with normalized data, the LSTM mean average error is about 0.008, and the ARIMA mean average error is about 0.014. So even the ARIMA model with normalized data performed better than the stateful LSTM model without normalized data. Thank you so much for listening to my presentation. I hope everything was clear. If there are any questions, please feel free to comment or reach out to me via email. And thank you very much.